We have covered many different topics on encryption, and this next lecture is going to cover encryption from a slightly different angle with a discussion on cryptographic hash functions. These functions provide a capability that enhances the use of encryption by adding a few additional features through secondary algorithms, which gives users even more capabilities. A cryptographic hash function, or hash for short, is a mathematical algorithm capable of generating a relatively short string of text from the contents of a file. This is a one-way algorithm, which means that it is infeasible to reverse the process, and it is considered to be a surefire way to verify a file hasn't been changed in transit. This is often used as a type of digital fingerprint for files, signatures, or other types of data that people want to authenticate as legitimate. The hash function adds another variable to encryption because encryption by itself does not provide any verification of the person who sent it, nor does it provide verification that the contents were not hijacked and changed in transit. The hash can help with this piece of the puzzle. Even the smallest of changes in a file will dramatically change the hash. So if someone was able to hijack a session, decrypt a message, change one word, re-encrypt the message, and send it to the original recipient, the hash would never match, and you would know that the message is not authentic. One of the ways this hash method is applied is to the digital signatures available in some email systems. A digital signature basically has a similar purpose as a hash. It exists to help a recipient verify the sender of a message. Digital signatures provide us with authentication, integrity, and non-repudiation. You may remember these terms from earlier courses, but let's quickly cover them again. Authentication is the process of identifying the source of a message. It gives us the ability to know that a message from Sally actually came from Sally and didn't come from Bob. Integrity gives us the assurance that the message has not been altered in any way. The one-way hash function changes dramatically with just a single character change. And non-repudiation establishes that a person who sent a message cannot later deny that they in fact were the ones who sent this message. Many nations have already established laws on the use of digital signatures which allow for them in official documents and records because of these three validation capabilities. A message authentication code, or MAC for short, is similar to a hash function, but it adds a few additional elements to make it significantly more secure against forgery attempts by adding additional algorithms to its overall design. But a MAC does not provide non-repudiation like a digital signature because the sender and receiver have to agree on the key being used before transmission occurs. And this key can be compromised during the agreement process, which would allow someone else to use it as well. Digital signatures are generated with the public key cryptography we discussed in an earlier lecture, which eliminates this problem. MACs are used in similar ways as hash functions and digital signatures. Think of them as a different type of fruit from the same basket. Many people over the years have developed different ways to accomplish similar tasks, and some are stronger in different environments. It's also good to have a choice in what can be implemented instead of simply being forced into using only one possibility. Creating a fingerprint for a file is probably the most common thing a savvy user may encounter on a regular basis when downloading files from the internet. Many security-conscious websites will provide the hash value for their download files so that a user can verify the hash after the download and before the installation. This is handy in case you happen to download the file from a different location because you can still check the hash to make sure it matches. For example, if a user in China is unable to download a file from the United States, but they are able to get it from a more local Chinese server, they can still verify its legitimacy or fingerprint using the hash function. If the hash doesn't match, the user will know it isn't the original file and should not install or open it because some type of malware may have been attached to it. Since the hash is a unique value, this method is extremely accurate. It is almost impossible to fake the hash or come up with a different hash from the exact same file. I say almost impossible because there's never any 100% certainty, but just as we previously discussed that AES is unbreakable because the resources don't exist today that can break it, a hash function falls into a similar category. There are two common algorithms that have been used for hashing for a long time. These two algorithms are known as MD5 and SHA-1. MD5 creates a 32-bit message digest from an input file and has been used since 1991. But it was found to have a problem in 2012. A 20-year run for a cryptographic function is pretty good considering the major changes in computing during that time frame. But the problem primarily affects what is known as being collision resistant, which could affect the legitimacy of a digital signature. SHA-1 was created by the National Security Agency and produces a slightly longer message digest of 40 digits, but it too was found vulnerable to a collision attack in 2005. Both of these hashes are still in existence today, and MD5 is still commonly found for creating password hashes in Unix and Linux-based systems, but it is believed to be strong for that purpose as long as the random data used to generate the MD5 is significantly long. Since both of these algorithms are effectively broken, something newer and more secure had to be developed. This is not uncommon in the cryptography world. You might be thinking that all of these cryptographic algorithms we have been talking about are insecure, but this isn't the case. The reality in our digital age is that as computing power increases, the chance of breaking something that was previously unbreakable also increases. The Caesar cipher was strong when it was used by Julius Caesar because the technology did not exist in his time to break the code. But it is worthless today because any user can download software that can discover its use and generate the clear text. And so it is the same today. 20 years from now, we will likely have some newer algorithms, and if quantum computing ever takes hold, the AES algorithm may also become vulnerable. But the nice thing is that the improved computing capabilities also gives us the ability to make stronger algorithms, so the problem and solution go hand in hand. SHA-3 is one of the most recent algorithms added to the hash family and was released in August of 2015. You may have noticed that I skipped SHA-2. SHA-2 was used to replace the insecurities of SHA-1. It is still considered to be a strong algorithm, but SHA-3 was created to provide a hash that was completely different from SHA-2, just in case a vulnerability was found in the future. SHA-3 provides an alternative for that just-in-case scenario. I want to leave you with some potential options of how you can use hash functions in your own communications to provide authentication, integrity, and non-repudiation where you may find it necessary or useful. The nice thing about encryption today is that it is available to anyone who can download the necessary software, and it is not only relegated to governments and large corporations with a lot of resources. OpenPGP is the most common distributor of open source encryption software that is freely available to the public. GPG4Win is an additional source that implements OpenPGP standards in their applications, and Encryptomatic provides plugins for Microsoft Outlook, as well as other applications that provide the ability to use digital signatures with a click of the button. Of course, with all of this software, you will need someone to communicate with that also uses encryption, otherwise your recipients won't be able to read anything you send. It's also important to note that most intelligence organizations who monitor internet traffic automatically store a copy of everything they find that is encrypted, simply because they think that one day they may be able to break it and read the contents. That practice likely won't stop anytime soon, so if you plan on using encryption, know that someone will be saving a copy of everything that you send. Okay, we have covered the hash algorithms that you can use and that are commonly used by most of the security conscious world, and now you should have a good understanding of how these options can be implemented on your own systems and networks, and how you can verify the legitimacy of messages and files. The algorithms at the top of the list today are very secure and unbreakable even by the best cryptographers in the world. So rest assured that until technology makes a giant leap forward, you can expect the continued capabilities these algorithms provide. And as I have mentioned at least one time already, the implementation of the algorithm is usually where the weakness creeps in. So only use software that is known to have good code and implements these capabilities properly.